Welcome to the Quarkside Quantum Physics Podcast, an exploration of the fundamental structure of reality, where quantum laws govern matter, energy, and information. Here, uncertainty is a feature, not a flaw, and understanding begins at the smallest scales.
Welcome back. Today we are going to try to wrap our heads around something that is simultaneously incredibly small and absolutely massive in terms of its implications.
That's a good way to put it.
We're talking about the future of computing, but, not the shiny marketing brochure version of it.
No, we are getting into the messy reality, the plumbing behind the palace, so to speak.
We always hear the grand promise, right?
Yeah.
We hear that quantum computers are going to solve these impossible problems, revolutionize medicine, crack encryption codes that would take a normal computer 1 billion years to solve.
Mm-hmm.
It's painted as this sci-fi utopia where the machine just knows the answer.
It is the ultimate promise of computational power. It's elite, not just a step. But
Yeah.
the gap between that promise and where we are today is, well, it's filled with some of the most difficult engineering problems in human history.
And today, we are going to zoom in on one of those problems,
Mhm.
way in.
Right down to the component level.
Past the headlines, past the hype, and right down to the microscopic reality of what it actually takes to build one of these machines. Because it turns out, building the future isn't just about big ideas.
Wow.
It's about controlling individual electrons in spaces that are only tens of nanometers wide.
It is an engineering challenge as much as it is a physics challenge. You're literally wrestling with nature at its most fundamental level.
How so?
Well, you're trying to force subatomic particles to behave against their natural chaotic instincts, to hold them still and get them to do useful work for you.
And we have a specific tension to look at today. We want to pack these things called quantum dots closer and closer together to build powerful computers. Because a computer with 2 bits isn't very useful.
Not at all.
But new research shows that these tiny neighbors are starting to, shout over each other.
Shouting is a very vivid way to put it. In the quantum world, shouting is more about energy exchange and frequency shifts. But the effect is the same. Distraction, interference, noise.
And we're basing today's discussion on a brand new study. It was published just yesterday, February 12, 2026, in Physical Review Applied.
Yes, this is coming out of the RIKEN Center for Quantum Computing. The research was led by Takashi Kobayashi and his team.
And RIKEN is a big deal in this space, right?
No, absolutely. RIKEN is a heavyweight in this field, so when they publish a paper on noise mechanisms, the community, it sits up and listens.
So what is our mission here? We aren't looking at a breakthrough where everything works perfectly. We are looking at a hurdle that was just discovered, or at least just precisely measured.
That's the key.
The goal is to understand what happens when quantum bits or qubits get too close for comfort.
It's a story about the growing pains of technology. To solve a problem, you first have to measure it precisely. That is what RIKEN has done. They haven't just found a problem, they've put a number on it. They've quantified it.
So we're building the supercomputer of the future, but the parts are arguing with each other.
In a manner of speaking, yes. But understanding that argument is the key to silencing it. Or perhaps, as we'll see later, even using it.
Okay, let's get into the nuts and bolts then. Before we can really talk about the noise, we need to understand the instrument. The study focuses on something called quantum dots.
Mm-hmm.
Now, I see that term, and my first thought is those high-end TV screens with the really vibrant colors. Are we talking about the same thing?
That's a great question, and it's a common point of confusion. It's the same underlying physics, yes, but for a completely different application.
Okay.
In a TV, a quantum dot is a semiconductor nanocrystal that's designed to glow a very specific, pure color when you hit it with light or electricity. It's an emitter.
It makes pretty colors.
It makes very pretty, very precise colors. But in a quantum computer, a quantum dot is a trap.
A trap.
Think of it as a potential well, a tiny, tiny region in a semiconductor material where we can confine a single charged particle, in this case, a single electron.
So you're catching one electron and holding it in place.
That's the entire goal.
Okay, so why silicon? I feel like when people see pictures of quantum computers, they see those beautiful big golden chandeliers, the superconducting quantum computers from Google or IBM.
Right.
Those don't look like chips, but RIKEN is using silicon.
That is a crucial distinction, and it really defines the different competing approaches. The chandelier computers use superconducting circuits. Those are, in electronic terms, quite large. They're macroscopic loops of metal cooled to extreme temperatures.
And what RIKEN is doing.
Well, RIKEN is working on what's known as silicon spin qubits. Looks much more like the chips you'd find in your laptop or your phone.
And the advantage of that is?
The hope is that because we already have, 50 years of experience and trillions of dollars of infrastructure for manufacturing billions of transistors on a silicon wafer.
Right, the whole semiconductor industry.
Exactly. The hope is we can eventually leverage all of that to manufacture billions of qubits the same way.
So it's a bet on scalability. If we can make it work in silicon, we can make millions of them and maybe make them cheap.
That is the long-term vision. But making a standard transistor is very, very different from making a quantum dot for a qubit.
How so?
Well, in a transistor, you're essentially just creating a switch for a current. You're controlling a river of electrons flowing through a channel, on or off.
A whole crowd of them.
A whole crowd. But in a quantum dot, you need to isolate one single electron from that river.
Just one.
Just one. And you need to hold it there very gently without disturbing its fragile quantum state.
Okay, so how do you build this trap? You can't exactly use tiny tweezers.
No, you use electric fields. It's actually quite clever. You fabricate tiny metal gates electrodes on top of the silicon wafer.
Like the gates in a normal transistor.
Very similar. But the arrangement is different. When you apply a negative voltage to these metal gates, they create an electric field that repels the electrons in the silicon underneath.
So you're pushing them away.
You're pushing them away. And by arranging these gates in a very specific pattern, like a little corral, you can create a small island, a box of low energy, surrounded by high energy walls. An electron can get trapped in that box.
So it's like using invisible force fields to build a jail cell for an electron.
A very, very small jail cell. We are talking about structures that are just tens of nanometers across.
And once the electron is in there, what are we actually using as the bit? In my laptop, it's voltage being high or low. That represents a 1 or a 0. What is it here?
Here we are using a fundamental quantum property of the electron. We're using its spin.
Spin. This is one of those quantum terms that everyone uses, but it's always a bit fuzzy. Is the electron actually spinning like a tiny top?
Not literally, no. That's just a helpful classical analogy. An electron is a point particle. It has no physical size to spin around.
So what is it then?
It's an intrinsic property, like its charge or its mass. It has an intrinsic angular momentum and an associated magnetic moment. It behaves as if it were a tiny spinning bar magnet.
A tiny magnet.
And that tiny magnet can point in different directions. For our purposes, we care about whether it's pointing up or down relative to an external magnetic field we apply.
Okay, so spin up is a 1 and spin down is a 0. Is that the basic idea?
That is the basis of it, yes. That's how you define your computational basis states. But because it's a quantum system...
It's not that simple.
It's not that simple. It can also exist in a superposition of both up and down at the same time until you measure it. That's where the real power comes from.
Right, the classic quantum weirdness. So just to recap, we have a silicon chip. We have tiny electric gates creating a trap. We catch one single electron. We use its magnetic spin as our data storage.
Correct. But here's the problem, the core vulnerability of this whole approach. That spin state is incredibly fragile.
What can mess it up?
Almost anything. The biggest enemy is thermal energy, just heat. Heat is just atoms and electrons jiggling around. If the environment is too hot, the electron shakes, it interacts with the lattice of silicon atoms around it, and the spin state just flips randomly.
Your data is lost.
Instantly. Your 1 becomes a 0, or your superposition just collapses. The information is gone. This is called decoherence.
So you have to freeze it.
You have to freeze it to near absolute 0. These chips don't just sit on a lab bench. They live inside a complex machine called a dilution refrigerator operating at temperatures in the millikelvin range.
How cold is that?
It is significantly colder there than in deep space.
So I should picture this. A giant humming silver cylinder in a lab. Inside it, there are layers and layers of gold and copper plates that get progressively colder and colder. And at the very bottom, in the deepest cold, sits this tiny silicon chip with these nanometer scale traps.
That is the exact picture, and that is where the RIKEN team is working. They aren't just looking at one dot, though. One qubit is a science experiment. A computer needs many.
And this is where we hit the scaling problem, the crowded house, as we called it.
Right. To perform calculations, to run an algorithm, qubits need to interact with each other in a controlled way. You need to be able to entangle them.
Which means they can't be miles apart.
They need to be close. Very close.
How close are we talking?
In the device in this study, the pitch, which is the distance from the center of one quantum dot to the center of the next, is about 100 to 150 nanometers.
That is incredibly tight.
It is extremely tight. And when you pack charged particles that close together, you run into a fundamental force of nature, the Coulomb interaction.
Remind us what that is.
It's the most basic electric force. Like, charges repel, opposite charges attract.
So 2 electrons.
2 electrons are both negatively charged. They hate each other. They are constantly trying to push each other away.
So I have 2 of these quantum dots right next to each other, and I've got 1 electron in each one. They're constantly pushing against the walls of their little jail cells, trying to get away from their neighbor.
Ideally, the electric field walls of the trap are strong enough to hold them in place, but they still feel each other's presence. The force is still there.
Okay.
So if the electron in dot A shifts its position slightly, and it has a little bit of wiggle room, maybe just by a nanometer.
The electron in dot B feels that.
The electron in dot B feels a change in the repulsive force. The push gets a little stronger or a little weaker.
It's like if you were standing in a small room with a powerful magnet strapped to your chest, and someone in the next room had one too. Even if there's a wall, if they take a step towards that wall, you feel a push.
That is a perfect analogy. And this brings us right to the core of the RIKEN discovery. Takashi Kobayashi and his team were investigating this exact scenario. They wanted to know, does that push from the neighbor mess up the information stored in the spin of our qubit?
And the answer, I'm going to assume, is yes. Otherwise, we wouldn't be doing this whole conversation.
The answer is a definitive yes, but the mechanism, the how, is the really fascinating part. Because it's not a direct effect. It involves a component we haven't even mentioned yet.
Oh.
The micromagnet.
The micromagnet. Okay, wait. Let's back up. We have electric gates to trap the electron. We have the electron itself acting like a tiny magnet with its spin. Why on earth do we need another magnet?
This is a great question, and it gets right to the heart of why silicon spin qubits are so hard to build and control. Remember, what we want to do is control the spin of the electron.
Right. Flip it from up to down or put it in the superposition.
Exactly. Now, spin responds to magnetic fields, so the obvious way to control it would be to zap it with a little magnetic pulse.
Seems simple enough.
It is if you only have one qubit. But remember, we're in a crowded house. If you want to build a real computer, you have thousands, maybe millions of these dots packed together.
And if I turn on a magnet, everything nearby feels it. It's hard to target just one dot without disturbing all its neighbors.
Precisely. It's called addressability. And it's a huge problem. You'd have magnetic crosstalk everywhere. So the engineers thought, is there a better way? We are very good at generating localized electric fields. We can switch voltages on those tiny gates incredibly fast and with pinpoint precision.
So they wanted to control the spin using electricity instead of magnetism.
That was the goal.
But can you even do that? I thought you said spin doesn't talk to electricity.
It doesn't, not directly. You need a translator. You need a physical mechanism that couples the electron's position, which electricity controls, to its spin state. This is a real physical effect called spin-orbit coupling.
Okay.
In some materials, like gallium arsenide, this effect happens naturally and is quite strong. In silicon, which we want to use for manufacturing reasons, it's naturally very, very weak.
So we have to fake it.
We have to engineer it. We create something called synthetic spin-orbit coupling.
Synthetic spin-orbit coupling. That sounds expensive.
It's clever engineering. This is why they install the micromagnet. They physically place a tiny strip of magnetic material, like cobalt, right on top of the quantum dots. But this magnet isn't designed to create a uniform field. That's the key. It's designed to create a gradient.
A gradient? What do you mean by that? So the magnetic field is stronger on one side of the dot than the other?
Exactly that. Imagine the quantum dot is a small room. The magnetic field at the left wall is, let's say, 100 units strong. The magnetic field at the right wall is 105 units strong. It's a slope. It's not flat.
Okay. I have a magnetic slope across my tiny room. Why?
No, remember, the frequency at which the electron's spin precesses, the speed at which it wobbles like a top, depends directly on the strength of the magnetic field it is sitting in. This is called the Larmor frequency.
So if the electron is sitting on the left side of the room, its spin wobbles at speed 100. If I move it to the right side, it wobbles at speed 105.
Precisely. Now you see the trick. We can use our electric gates to gently nudge the electron's position. If we apply a little voltage, we can push it from the left side of the dot to the right.
And by pushing it, we force it to move into a stronger part of the magnetic field.
Which changes its spin speed.
So we are using electricity to move it, but it's the motion through that pre-engineered magnetic gradient that actually changes the spin.
You've got it. The micromagnet acts as a translator. It converts an electric signal, which is a change in position, into a magnetic control, which is a change in spin rotation speed. It acts as a lever. It makes the electron's spin highly sensitive to its physical location.
That sounds brilliant.
Yep.
It's a really clever workaround. Problem solved, right?
It is brilliant. It's a technique called electric dipole spin resonance, or EDSR, and it allows for very fast, localized control of individual qubits. But
There's always a but.
there is no free lunch in physics.
I knew it! Here comes the bill.
By making the spin exquisitely sensitive to its own position, you have also made it exquisitely sensitive to anything else that might shift its position.
Like the neighbor pushing on the wall.
Like the neighbor. Let's go back to our crowded house. We have two dots, dot A and dot B, side by side. Each one is sitting under this micromagnet gradient.
Okay.
Now, suppose the electron in the neighboring dot A moves. Maybe we're performing an operation on it, or maybe it just jiggles because of some background charge noise.
The neighbor moves the sofa.
The neighbor moves the sofa. When that electron in dot A moves, the Coulomb repulsion it exerts on our electron in dot B changes.
The push gets stronger or weaker.
And because our electron in dot B is sitting in this carefully balanced electric trap, that tiny change in push from the neighbor is enough to shift its position slightly.
And because of the micromagnet gradient, when our electron moves,
It moves into a different magnetic field strength.
and therefore,
Its spin frequency changes.
bingo. The neighbor's motion has changed the speed at which our qubit is spinning. This is the crosstalk. This is what the RIKEN paper calls a charge-induced spin frequency shift.
That's it in a nutshell.
So the micromagnet is a complete double-edged sword. It gives us the precise control we need, but at the same time, it acts as an amplifier for the noise coming from the neighbors.
That is the crux of the problem they investigated. You built a system that is hypersensitive to motion, so you could control it with electricity, but now it's hypersensitive to the unwanted motion of the guy next door.
Okay, so this sounds bad in theory, but was it just a theoretical worry, or is it actually messing things up in a real device?
That is the billion-dollar question, and it's what Kobayashi's team went to find out. They didn't just model this on a computer. They built the device, they cooled it down to 100 millikelvin, and they measured it directly.
Wow.
And the way they measured it is fascinating in itself.
I was going to ask, how do you measure a tiny shift in the wobble frequency of a single electron trapped in a piece of silicon?
You use a very sensitive technique called Ramsey interferometry.
Ramsey interferometry. Is that related to Ramsey kitchen nightmares?
No relation, though it can be a nightmare if you don't get the calibration right. It works a bit like this. You start with the electron spin pointing up. Let's call that our starting line.
Okay.
You hit it with a precisely timed microwave pulse that puts it into a perfect superposition, half up, half down. Now, you can picture its state as a clock hand pointing, say, at 3 o'clock.
Got it.
And then you just wait. You let it evolve. That clock hand starts sweeping around at its natural frequency, the Larmor frequency.
Tick, tick, tick.
You let it tick for a very specific amount of time. Then you hit it with a second identical microwave pulse. If the frequency was exactly what you thought it was, this second pulse will push the clock hand all the way around to point down.
So you know exactly where it should end up. It's like checking your watch against a master clock.
Exactly. But what if the frequency has shifted during that waiting time? What if the neighbor moved, pushed our electron into a stronger magnetic field, and made the clock tick a little faster?
Then the hand won't be where you expect it to be.
It will have rotated too far. When you hit it with that second pulse, it won't end up pointing down. It'll be somewhere else. This difference between where it is and where it should be is called a phase error.
And in quantum computing, phase is everything.
Phase is where the information is stored in many algorithms. If the phase drifts uncontrollably, the calculation is wrong. It's a fatal error.
So what did the RIKEN team do with this technique?
They performed this Ramsey experiment over and over again. But while our qubit's clock was ticking, they were deliberately moving the neighboring electron back and forth using its control gate.
They poked the bear just to see if it would growl.
And it did. They observed a clear, perfectly correlated shift in the qubit's frequency that matched the movement of the neighbor electron. When the neighbor moved closer, the frequency went up by a specific amount. When it moved away, it went down. They mapped it out precisely.
So it's not theoretical anymore. It's a hard number.
A quantified, measured effect. This is the first time this specific mechanism has been directly measured and isolated.
How bad was it? Was it a tiny blip, something you could maybe ignore?
According to the paper, the shift is large enough to cause a considerable qubit error rate.
A considerable error rate. That doesn't sound good.
It's not. We measure the quality of our quantum operations in terms of fidelity. A perfect operation has 100% fidelity. To make a fault-tolerant quantum computer work, you need operation fidelities of 99.9%, or really 99.99% or higher.
So you can only have one error in 10,000 operations.
At most. This crosstalk mechanism introduces errors that can easily drop you well below that threshold.
So this isn't just background hiss we can filter out.
Yeah.
This is a potential showstopper. If you can't fix this, you can't scale up to a large number of qubits.
Showstopper might be too strong, but it is definitely a gatekeeper. It's a problem you cannot pass until you solve it. If you try to build a chip with 1 million qubits, and they are all shifting each other's frequencies every time they move,
You just have a million sources of noise.
you don't have a computer, you have a very expensive, very cold, random number generator.
Which is useful for casinos, maybe, but not for curing cancer.
Exactly. This is what the paper refers to when it says this problem prevents the silicon quantum computing community from realizing a large-scale device. It's a roadblock.
So we have identified the villain. It's this unlucky combination of the crowded neighborhood, the Coulomb interaction, and the very sensitive amplifier that we put in for control, the micromagnet.
That's the mechanism.
Now, usually when engineers find a source of noise, they try to eliminate it. They add shielding, or they redesign the parts to be further away. Can we do that here?
Well, moving them further away is a non-starter. You lose the ability to entangle them, which you need for computation.
Okay, so that's out. What about shielding? Can you put a little wall between them?
Shielding electric fields at the nanoscale inside a solid piece of silicon is incredibly difficult. It's not really a practical solution right now. So Kobayashi and his team suggest a different approach in the paper.
What's the plan?
The plan has two parts. The first is mitigation. The second and more exciting part is exploitation.
Mitigation and exploitation. Okay, let's start with mitigation.
First, the key discovery here is that we have quantified it, we have measured it, we can predict it.
Right. It's not random noise. It's correlated noise.
That is the key word. Random noise is a nightmare to fight. It's like trying to have a conversation in a room with 1,000 people talking at once. But if the noise is correlated, if I know that every single time neighbor A moves to the left, my qubit B is going to shift its frequency by exactly 5 megahertz, then I can do something about it.
You can compensate for it.
Exactly. This leads us to a strategy called feed-forward correction. The classical computer that controls the quantum chip can be programmed with this knowledge.
How would that work in practice?
When the control system sends a command pulse to the gate of neighbor A telling it to move, it can, at the exact same time, send a small corresponding correction pulse to the gate of qubit B.
It's like noise-canceling headphones.
That's a fantastic analogy. Noise-canceling headphones have a microphone that listens to the outside sound, and then the electronics generate an inverse sound wave to cancel it out in your ear. Here, we don't even need to listen. We know the frequency shift is coming because we're the ones causing it by moving the neighbor. So we can preemptively adjust the dial, the control voltage on qubit B to counteract the effect precisely as it happens.
So you fix the error before it even has a chance to mess up the calculation.
Ideally, yes. You can program these corrections right into the gate operations. It adds complexity to the control software, but it's a viable path forward.
Okay, that makes sense. That's the mitigation. What's the exploitation part?
This is the part that I find most exciting. Kobayashi's team suggests that instead of just canceling this effect, we might be able to use it.
Use the noise. How?
Well, think about what this crosstalk effect actually represents. It is a form of coupling. It is a connection between two qubits that were not supposed to be directly interacting.
Right. Qubit A is talking to Qubit B even if we didn't want it to initially. It's an accidental phone line.
And in quantum logic, what do we need to do? We need to perform two qubit gates. These are operations where the state of one qubit conditionally changes the state of another. That is how you build logic. That is how you build an algorithm like Shor's algorithm for factoring.
So normally you have to work really hard to force them to talk to each other in a controlled way.
Yes. A common way is to physically lower the electric potential barrier between them, let their electron wave functions overlap, and let them interact via something called the exchange interaction. It's tricky and has to be managed very carefully.
But here,
the micromagnet has accidentally given us a new long-range interaction. They are talking to each other via the magnetic gradient and the electric field, even when their wave functions aren't touching.
So the researchers are basically saying, don't mute the crosstalk. Let's try to turn it into a high-fidelity phone line.
That's it. The paper suggests this could lead to a new class of qubit operations. If you can control this energy shift precisely, if you can turn it on and off by moving the neighbor electron, you could potentially use it to perform logic gates between qubits that are not immediate neighbors.
So you could do a calculation between qubit A and qubit C, using qubit B's position as the switch.
That's the kind of new capability it might open up. You can turn this bug into a feature.
That is the ultimate engineering judo move. Use the force of the problem itself to solve the problem.
It connects to the broader history of developing these silicon qubits. Time and again, we're finding that things we initially thought were bugs, things like subtle variations in the silicon crystal, the valley splitting, or roughness at the silicon oxide interface, and now this micromagnet crosstalk can sometimes be understood, controlled, and engineered into resources.
If you understand the physics deep enough.
If you understand the physics deep enough, it's a testament to how mature the field is getting. We're moving from just trying to get one qubit to work to understanding the complex, multi-qubit interactions in a large system.
It seems like a constant race between the problems we discover and the solutions we invent.
It is. The silicon quantum computing community, as the text calls it, is in a fierce but friendly race against the superconducting folks and the trapped ion folks.
Different horses in the same race.
Right. And silicon has this massive theoretical advantage of manufacturability, but it has these complex material physics challenges that the other platforms don't. This study is a major step in clearing the fog around one of those challenges.
So let's just zoom back out for a second. We started with single electrons shivering in the cold. We built an electric jail cell to trap it. We gave it a special magnet to control it. We then realized that magnet made it listen to its neighbors too much. We then figured out exactly how it was listening, measured the volume, and now we are planning to turn that unwanted listening into a controlled conversation.
That is a beautiful summary of the scientific process right there. We went from identifying noise to potentially creating a new kind of signal.
Why does this matter to the person listening right now? They might be driving to work or doing the dishes. Why should they care about the Larmor frequency of a single electron spin?
It matters because it peels back the curtain on how progress in technology actually happens. We often get this very clean, linear narrative of progress. We think of technology as just this inevitable march of better, faster, cheaper.
But it's not like that at all.
It's not. It's a messy, winding path. It's a series of roadblocks. It's discovering that your clever solution, the micromagnet, caused a brand new problem, the crosstalk. It's the painstaking, unglamorous work of measuring and characterizing that problem.
It's less of a eureka moment and more of a, that's weird moment, followed by a year of work.
A year of very careful work in a very cold room. And it's the realization that you cannot just build it and hope it works. You have to understand the fundamental physics of the noise, of the imperfections.
And it really grounds the hype around quantum computing. This isn't magic, it's plumbing. It's just extremely high-tech, atomic-scale plumbing with very leaky pipes.
It is. And for anyone interested in the future of computing, watching how the community solves these very specific hurdles, like the crosstalk challenge that RIKEN just mapped out, is a much better preview of the future than any marketing material. This is where the real work is happening.
If they do solve this, if they can either cancel this crosstalk perfectly or turn it into a reliable tool, does silicon win the race?
Win is a strong word. There might be room for multiple technologies, but if they solve this, silicon becomes a terrifyingly strong competitor.
Why terrifyingly?
Because if you can handle this crosstalk, and you can solve a few other known materials issues, and you can make these things using standard semiconductor foundries, the scaling potential is just massive. You could genuinely have millions of high-quality qubits on a single chip the size of your thumbnail.
Whereas the golden chandeliers, as beautiful as they are, take up a whole room for a few hundred or 1,000 qubits.
Exactly. Density matters for building a truly large-scale, error-corrected machine.
So I want to leave the listener with a final thought, something to chew on. And it's about this idea of interconnectedness.
Chew on?
We tend to think of isolation as the ideal state, right? In our daily lives, we want peace and quiet to focus. In quantum computing, the mantra is always isolate your qubit, so it doesn't decohere and lose its information.
Isolation preserves the quantum state. That's rule number one.
But a computer that is perfectly isolated does nothing. It's just a perfect box of secrets. To compute, to do anything useful, you must connect. You must have interactions.
Information is physical, and physics is, at its heart, the study of interactions.
So this struggle that the RIKEN team is documenting, this push and pull between keeping the qubit safe from its neighbors, but also needing it to talk to its neighbors, it's not just an engineering problem. It feels like the fundamental tension of the universe, doesn't it?
In a way, it is. For any information processing system, it is the balance between coherence and coupling. Too much isolation, and your system is useless. It can't process anything. Too much connection, and it just becomes noise. Everything washes out. Finding that sweet spot, that perfectly controlled interaction, is the whole game.
And RIKEN just showed us exactly where that line is drawn for this type of device.
They gave us the map of a new part of that territory. Now the community has to figure out how to navigate it.
Well, my brain is suitably entangled. Thank you for walking us through the nanoverse today. This was fascinating.
It was a pleasure. It's always good to look at the small things that make the big things possible.
We'll see you in the next one. Keep learning.
Stay curious.